Hello everyone. Today I'll be presenting the topic of round-robin CPU scheduling algorithm, one of the most widely used CPU scheduling algorithm, especially for the time-sharing system. By the end of this presentation, you will understand exactly what the round-robin is, why we use it, and how it executes process fairly and predictably. So, what is round-robin? Let's begin with a definition. Round robin is a preemptive CPU scheduling algorithm. That means that the CPU time is sliced into small intervals and distributed equally among the processes. Think of it as everyone waiting in a circle. Each process gets its turn for a fixed period, then passes control to the next process, repeating in cyclic order. It's extremely popular in time-sharing system, those where we want the system to feel responsive for all users, like Unix, Linux, and modern web servers. Its simplicity and fairness make it perfectly for interactive computing where many processes need to share CPU time without any one process hogging the CPU. So each process receives a small unit of CPU time. A unit is called time quantum. Time quantum is what which makes round robin different from other CPU scheduling algorithm. The time quantum is typically between 10 to 100 milliseconds. The round-robin process executes in a cyclic order, in which the process which enters first in the queue will be executed first. The CPU switches after the time quantum expires. The key concept in round robin is the time quantum, the small fixed time slice each process is allowed to run. Typically, the time quantum is 10 to 100 milliseconds. If a process finishes before its time quantum expires, the CPU moves on immediately. Otherwise, the process is preempted after this quantum and move to the end of the queue. You can imagine this like everyone standing in a queue to use their computer for a short fixed time. After this computer, they must go to the end of the queue if they need more time. That's round robin in action. As I've already told you, time quantum is a main concept of round-robin scheduling, a fixed time for process to execute. It's typically between 10 milliseconds to 100 milliseconds. Ready queue, in which process waits for their turn to be executed while the CPU is performing other process. We can imagine it like a waiting chair where big processes are waiting for their turn. Context switching. Every time the CPU switches to new process, the system must save the old process state and load the new one. This introduces overhead. Process completion. Process management. Once a process finishes before its quantum is up, it leaves the queue. Otherwise, it is placed at the back of the queue. So now let us look at some advantages of round-robin scheduling. Every process gets an equal shot at CPU. There is no starvation. That's why this algorithm is fair algorithm. Good for short jobs. Interactive and short jobs get a quick response. Simple and predictable. Easy to implement and understand. The wait time is bound. With some advantages, there are some disadvantages of round-robin scheduling. Context switching overhead. Too many switches can decrease CPU efficiency. Sensitive to quantum size. Too short a quantum means too much overhead. Too long means poor responsiveness. Poor for highly varying burst times. Longer jobs may wait much longer. So let us put this into practice with an example. Imagine we have four processes P1, P2, P3 and P4 and the following burst times and the arrival times. The arrival times of processes P1, P2, P3 and P4 are 0, 1, 2, 3 and burst time of each process is 5, 4, 6 and 3 and we can see time quantum is given to us as 2 milliseconds. So now we will solve this numerical for better understanding. To solve this question, we need a ready queue and a Gantt chart. So uh, this is a ready queue and this is our Gantt chart. So we know round robin works on first in first out execution. So we will see which process we entered first. So we can see here that P1 is entered at time 0. So first process 1 will enter into this ready queue for its turn, and we can see it's the first process and there is no process executing right now. So P1 will be executed into a Gantt chart first. So P1 will enter the Gantt chart and will be executed for the given time quantum, which is 2 seconds. So it will start from 0 to 2. Now in this time interval 0 to 2, we will see how many other processes entered the ready queue. So we can see from 0 to 2 there are two processes entered the ready queue, which is P2, which is arrived on one time, which is somewhere here. So we'll write P2 is already waiting in ready queue, and P3 is also in the ready queue, which come at time 2. So when the one process is executed, it will go again into the ready queue if its bus time is remaining. So the bus time of process 1 was 5, but now 2 of it is executed. So 5 minus 2 will be 3. So now the bus time of process 1 is 3, and it will be subtracted by 2 until it's completed. So now we'll see which is the next process. So we can see P2 is next. So then P2 will enter the Gantt chart, and it will also execute for 2 millisecond. So it was 2 and now it will be 4. And now we'll see between 2 and 4 how many other processes entered the ready queue. So we can see between 2 and 4 the P4 is entered in ready queue already. So P1, P4 is also waiting for his turn here. Now P1 is executed, P2 is executed, and we will subtract 2 from the bus time of P2. So 4 minus 2 is 2. Now we'll see, now P2 will again enter the ready queue. Now it's P3's turn, so P3 will go into the ready queue. Oh, Gantt chart. And it will also be executed for 2 milliseconds. So for P3 it's now not 6, it's 4 now. And now P3 will again enter the ready queue. So I think we have forgot to put P1 into ready queue again, so we are doing it now. The P1 is waiting here before P4. So now after P3, P1 will be executed. So we'll cut P1 from here, and P1 is now again executing for 2 seconds. So from 6 it will be 8 now. And now the bus time of P1 will be 3 minus 2, which is equal to 1. So bus time of process 1 is 1, and P1 will again enter the ready queue to execute its one remaining bus time. So after P1, P4 will execute for 2 seconds. So it will be 10, and this 3 will be 2. So now after P4, it's P2's turn. So P2 will be executed for 2 seconds, which means for 12. And where is P2? And so P2 is completely executed. We can see here its bus time is 0 remaining, means it's executed, and now it will be out of the execution process. So now P3 is remaining, and we again forgot to write P4 here, so P4 is waiting here. Now after P2, P3 will be executed. So P3 will execute it for 2 seconds again, so it will be 14, and this will be 2. After, and P3 will again wait for his next turn in ready queue. So it's P1's turn again, and P1 is remaining only with the 1 second, but we can see the time quantum is 2. So what will happen? So the process will be executed for its remaining 1 second, not for 2 seconds. So here P1 will be executed for only 1 second, so this 14 will become 15. And P1 is also out of the execution process because burst time is 0 now. Now only two processes are remaining, P4 and P3. So now it's P4's turn, and P4 will be executed for 2 seconds, and P4 is also 0, so it's also out of the execution process. Now only P3 is remaining for 2 seconds, so we'll execute P3 for. So now we have to remember the completion time of every process. Like P3 is completed on this time 18. So we have the completion time of P3 is 18, and we have to remember the completion time of every process. Like where P2 is completed. P2 is completed on time 12. So 12 is its completion time, and we have to remember the completion time of every process. And this is what I explained above with like how we have to solve in copy. This is just a structure of how we have completed this. So as we can see, the AT of each average arrival time of every process is given, and burst time of every process is also given in the question. Now we will remember the completion time of every process, which is 16, 12, 18, and 15. So now we have to find the turnaround time and waiting time. So how to find turnaround time? The formula for turnaround time is CT minus AT. So when you subtract completion time and arrival time, you will get the turnaround time. So here we will subtract 0 from 16. So 16 minus 0 is 16, 12 minus 1 is 11, and 18 minus 2 is 16, and 15 minus 3 is 12. So here we have got the turnaround time of every process. Now we'll find the waiting time. So the formula for waiting time is turnaround time minus burst time. So when you will subtract burst time from turnaround time, you will get the waiting time. So 16 minus 5 is 11, 11 minus 4 is 7, 16 minus 6 is 10, and 12 minus 3 is 9. So here we have also got the waiting time. Now we will find the average turnaround time and average waiting time. So to find average waiting time, we have to add all the turnaround time of every process and divide it by number of process. So we'll add 16 plus 11 plus 16 plus 12. We have done it here and divided by number of process. So how many process we are having? So we have four processes. So when we divide we will get 13.75 as average turnaround time, and we'll do the same for waiting time. So we will add all the waiting times, which is 11 plus 7 plus 10 plus 9, and divide it by number of processes, which is 4. So we will get the 9.25 millisecond as average waiting time. So this is fairly typical for round robin. It's not as optimal as shortest job first for minimizing wait times, but it provides equal opportunities to all processes. This is exactly why it is preferred for interactive or time-sharing environments like multi-user operating system where responsiveness matters more than absolute drop. So to conclude, round robin is most appropriate for time-sharing operating systems like Unix and Linux. Interactive applications like web server desktop operating system where we want to quick response time, balance load between process so nobody starves. Just remember, turning the time quantum is important. Too small quantum waste time on context switches. Too small a quantum waste time on context switching. Too large and you will lose the responsiveness. So the choice is trade-off between CPU efficiency and response times. So this is all from my side. Thank you for your attention and listening me.